Hey Molly, this is Dan Cumpry. I am your dad's friend. I teach at his school, and I live a couple houses away from your Grandpa Mike Heimbach, who, by the way, stopped me in the road yesterday and said, "Really? You're going to be doing some math with my granddaughter Molly? Be sure to tell her. Make sure that when you're done there, Mr. Cumpry knows that a Heimbach had been there." All right, are you ready? So I asked your dad what this process looked like that you that you learned somewhere. And this is the example that you and your dad shared with me. For a quadratic trinomial whose blue coefficients are all integers, like 3x squared minus 7x plus 2, you've learned several ways to factor this into two binomials with integer coefficients. I'm going to be a little nitpicky about a couple things on this example. First of all, this should be a 2 right here, so I'll go ahead and correct that. And then on the right side, this grid method you're using is really cool. It's really interesting, and the main question your dad asked me at the time was, does this always work? So can you trust that you can use this moving forward? And the answer was yes, it does. And the second question was, why does it work? Because it seems pretty strange. But since you asked, let's figure out why it works. All right. Being a little more nitpicky, on the right side of the page, you put the A term at the top of the grid right here. And then I see that you put the B term right there. And this 6 came from obviously multiplying A times C. So the thing that I'm going to be a little nitpicky about is instead of putting a B here, I'm going to put something else. Notice in this little grid, the products of the first two numbers horizontally equal the third number, the number in the margin. 3 times -2 is -6. Horizontally, that works everywhere. 1 times -1 is -1. But also the products of these two numbers vertically are equal to the number at the top in the margin. So 1 times 3 is 3. -1 times -6 is 6. Oh, but this doesn't work. The -7 serves no purpose here. Now what really is here is the C term. So in this chart, instead, let's think of putting the C term there. It doesn't change your result in the end, but it does make everything consistent. So the A term will go in the chart, the C term will go in the chart, which in this case is 2. And now we've got consistency everywhere. Horizontal products equal the number in the right margin everywhere. And vertically going up, the product is equal to the number in the margin at the top everywhere. All right. So I just wanted to go over those couple of things from this example you shared, but now let's get into it. So go ahead and use your strategy to practice this problem again. Let's factor 8x squared plus 13x minus 6. So go ahead and pause the video, and once you're done, come on back and hit play. All right, so you've got your answer, and I'm going to walk through your process and see if I've got your process right. For a quadratic trinomial that we know does factor, our strategy would be to make that little x, and we'd put, let's say, the 13 on top. That was the B term. And then the A term times the C term on the bottom. 8 times 6 is -48. And then we're looking for two numbers which add up to give us 13, and they multiply to give us -48. So I trust that the numbers you came up with were, let's say, 16 and -3. They add to 13, and they multiply the -48. All right. Using your really cool grid method, we would go ahead and make this grid. And in the top, we put the A term, the C term, and the AC term. And on the right margin, we'd use those two numbers you have from that X grid, the 16 and the -3. All right, then whatever two numbers are in these blank boxes have to multiply to give us 16, and these two have to multiply to give us -3. So clearly, this one's going to be easier because our only options are 1 times 3. Of course, 1 will be negative. All right, which one should we put where? Well, you can't put a 3 here because there will be no way to multiply integers and get 8. So we'll reverse that and put the 1 there and the 3 there. Now one of these has to be negative so that the horizontal product is -3. Let's just move up to the vertical products. 1 times 8 will give us 8. And 3 times -2 will give us -6. But one of these has to be negative for this horizontal product. So if we make the 3 negative, everything works. 8 times -6 is -48. 8 times 2 is 16. 1 times -3 is -3. 1 times 8 is 8. -3 times 2 is -6. And -3 times 16 is -48. Everything works. And now we can put it together the way you did this little fancy cross-multiplying thing. But we attached an x to that 8. So we had 8x and the -3. And then using this arrow, 1x and 2. And there it is. There's our answer. We factored it. And it will work every single time. As long as this quadratic trinomial is factorable, this strategy will work every single time. All right, now for what I think is the interesting part. Why does that work every time? A lot of weird, interesting things going on, both with this little puzzle we solved in green, and then this little puzzle that we solved in green, and then the way we threw it together in the end. Why does this work? Well, to show and convince ourselves why that works, we're going to have to be very abstract. We won't be using any numbers. We will only be using variables. Are you ready? All right. All right, so ax squared plus bx plus c is factorable into product of two binomials. So next we're going to multiply out these right two binomials. And if you like, you can pause the video and do that on your own, and then come on back when you finish. All right, so if we multiply those two binomials out on the right side, the first term times the first term will be dx multiplied by fx. First term times the first term. All right, now let's do the first term times the last term, or the outside products. Dx times g. And you don't need to use parentheses the way I am. There's more than one way to write these expressions. All right, so now we've effectively distributed the first term times everybody in this, like that. And now we have to do it with the e. So e gets multiplied by the f of x, or we can think of that as the inside product, inside times inside. So we have e times fx, and then e gets multiplied by g. So we could think of that as the last term times the last term. Again, you don't need parentheses here. So we just used the distributive property. Some teachers like to teach that as the FOIL acronym. But in any sense, let's go ahead and rewrite some of these things here. Notice on the left side, this quadratic trinomial really only has one variable, x. And there's an x squared term and an x term and a constant term, or an x to the 0 term. The red parts are coefficients. So I'm going to rewrite this expression here with black x terms and red coefficients. And I'm going to be using the associative property of multiplication here, which means when you multiply things like d times x times f times x, you can change the order of those factors. All right, for this term, we'll write the d times the f, and then oops, I wanted to do that in red. Our coefficients will be in red. So the d times the f, and then we have times the x, which is x squared. All right, so here we have d times x times g. Changing the order, we can rewrite that as d times g times x. Doing the same thing with this term, we can rewrite this as the e times the f times the x, where the e and the f are the coefficients, and the variable is x. And then for that last term, we have e times g. There's no black variables of x. All right, now there's one more thing we're going to do here. We're going to combine like terms. Now, just like if you had 3x and 5x, you would combine those to be 8x because they're like terms. What really allows us to do that is the distributive property. We can factor out the x and do 3 plus 5. It just makes sense that 3x's and 5x's is 8x's. But technically, we're using the distributive property, x times 3 plus x times 5. We can do the same thing here, and it will look like this. dg and ef all multiplied by x. All right, this is where I want it to be. All right, at this stage, let's make some observations. This expression is equivalent to this expression. There's 3 terms here. There's 3 terms here. 1, 2, and 3. This is our constant term, just like this is our constant term. So C is equal to EG, and we can write that down. The coefficient on x squared, they're equal. DF must be equal to A. And finally, the coefficient on the x term is dg plus ef. Now, the coefficient on the x term is b. Those coefficients must be equal. So b must be equal to dg plus ef. And at this stage of the game here, we can answer one of the mysteries of this process. Why do we multiply the a times c? Why does this play such an important role? So if we were just exploring this relationship when we factor a quadratic trinomial, and if we went through what we just went through, we would make an interesting observation, and that is that A's factors, D and F, show up in B's expression. C's factors, E and G, also show up. If we multiplied A times C, we would get EG multiplied by DF. What do we see here? That there are 2 numbers which add up to give us our B coefficient and multiply to give us the product of our A and C coefficients. Because of course we can, using again the associative property of multiplication, we can rewrite this as D times the G times the E times the F. So in order to factor this quadratic trinomial, we're looking for 2 green values which add up to give us B and which multiply to give us AC. And so mystery number 1 is unraveled. That's why we multiply A times C, and that's why this plays an important role. All right, so now let's get to this. Well, let's do the X issue first. So when we solve this little puzzle, we put the B coefficient on top and A times C in the bottom. So let's do that here. We're going to put the B coefficient on top. and the A times C on the bottom. And then we had to find two values which added to give us B and which multiplied to give us AC. Well, the values will be DG and EF. So let's write those in. I mean, we already knew that just from the algebra, but using this pattern, we can see that if we add DG plus EF, we do get B. And if we multiply DG times EF, we do get AC. All right, so next comes the grid. We'll go ahead and make this grid. All right, and then we placed our A coefficient there and the C coefficient there. And following our multiplication idea, horizontally, A times C is what goes there. All right, and then what do we do? The answers to this question we put in this column. Well, our answers to that question are DG and EF, so we'll put those here. All right, so vertically, if we multiply EF times DG, do we get AC? We sure do. All right, what about this way? So we're going to have a D here and a G, or maybe a G and a D. So should we put the D or the G factor in this first column? Looking at A is DF. There's no G in A's product, but there is a D. So the D goes first for sure, no doubt about it. D goes there, which means this has to be a G. All right, now we know that A is equal to DF, so A will be equal to D times F. We know that C is equal to E times G, so C will be equal to G times E. And let's just do a quick check. The multiplication should work everywhere. It works here, D times G, check, F times E, check. F times D is equal to A. Yep, check. E times G is equal to C. Yep. And EF times DG is equal to AC. Yes. All right, so at this stage, what happened next? We said DX and E. Multiplied by, then we went this way, FX and G. And is this what we needed? Is this the answer? And the answer was, yeah, if this factors into the product of two binomials, and we're trying to find out what those two binomials are, how do you factor this trinomial? Then we just proved that when you go through this process with the x's and the grids, we proved that we will always get the right answer. And in algebra's abstract but beautiful kind of way, this proved why it always works. I'm not sure, since we're not working together live right now, what the expressions on your face have been, if this is all making crystal clear sense, or if a lot of this seems abstract, and you might want to just spend some more time thinking about it, maybe watching the video again. Maybe after you do that, take a blank piece of paper and see if you can prove the whole thing on your own. Well, I hope this made some sense. I hope you found it interesting. If you understand it clearly and could actually explain to somebody with a blank sheet of paper already, then that's amazing. That'd be great. 99.9% of my students, though, would not be able to do that yet. They would need to spend a little more time thinking about it and maybe actually practice it. Well, I've got a challenge for you, and that's going to come on the next slide. All right, do not start this challenge until you feel confident that you understand everything that happened before. Do not start this challenge until you could take a blank sheet and actually explain why your method works to somebody. And if you didn't like that, then don't start this challenge at all. But if you liked that, then I would challenge you to use the same sort of ideas to explore why the following procedure works. Because this one's pretty weird, but the proof or derivation of why it works is actually pretty similar to what we just did, but it'll be different. So it'll be more exciting for you to try it on your own if that kind of thing appeals to you. And it doesn't need to appeal to you, but if it does, I think you'll really like this. All right, let's use the same example. We're going to factor 8x squared plus 13x minus 6. So I don't know if you've ever seen this. I actually didn't see it for the first 25 years of my career, and then somebody showed it to me, and I was like, whoa, that's weird. And they didn't understand why it worked, so I went through what you and I just went through and showed why it worked. And here's how it goes. This strategy says, if this quadratic trinomial is factorable, then we can factor it by completely rewriting it with no coefficient on the x squared term but 1x squared. However, we do need to multiply that 8 times the negative 6 again. So we have a completely different quadratic trinomial, but the leading coefficient is 1, and we change the constant to the leading coefficient times the constant. All right, now what? Well, this is going to be factorable. How do we know for sure? Well, you'd have to prove that using variables like we did before. How do we know that if the first quadratic trinomial is factorable, then the second one is also factorable? Well, that's something you can try to prove on your own. All right, so we'll factor this one, which is easier because the lead coefficient is just 1. And the answers to what comes next are the same answers as what you did in that x puzzle, which are 16 and 3. So we'll do plus 16 and minus 3. All right, then what? Well, that 8 coefficient that we just sort of erased in the beginning, we're going to rewrite it in the problem as denominators under these constant terms. And then we're going to simplify those fractions if we can. And 16 plus 8 is 2. And x minus 3/8, if it were a reducible fraction, we'd reduce it, but it's not reducible, so we'll just leave it. And then after you've reduced the fractions, simplified them, if you have any denominator, you just simply rewrite that right there. And you might notice this is the same answer we've got before. So the challenge question here is, oh my God, why can you take a factorable quadratic trinomial, just drop off the lead coefficient, but multiply it by c, factor that, reduce the fractions if possible, this one reduced, this one didn't, and if a fraction doesn't reduce, just take that denominator and put it up front in that binomial. Why does this work? And that also will work every single time. Well, if you give it a shot, I would love to see your proof. If you give it a shot and you're not quite sure how to prove it, I would love to get back together with you and maybe work through the proof of why this interesting strategy also works. Well, Molly, have a great school year, and maybe I'll hear back from you. Otherwise, take care. And remember, always make sure that they knew a Heimbuck was there. Grandpa Heimbuck.